Welcome to section 4.7, Optimization Problems. In this section, we will see how to apply what we've learned in chapters 3 and 4 to real-life problems. So this is very prone to having word problems. So it's often regarded as difficult by students, but it should be seen as rewarding because now we can apply what we've learned to real-life situations. In the first exercise, we have a packaging company that is contracted to make boxes by cutting squares from the corners of a 20 by 25 centimeter piece of cardboard. So this is the piece of cardboard, and we are going to cut little squares at each corner. Once we do that, the flaps are then folded up to make an open box. So we can fold these flaps. This is one of the flaps, this is another flap, and the fourth flap, and so when we fold them up, we get an open box like this. What is the maximum volume possible for the boxes? So, if we cut tiny squares at each corner, the benefit is that the base of the box will be very wide. The base, so the inside or the bottom of the box will be very wide. However, in exchange, we lose quite a bit in terms of height. It won't be very high. Or if we cut very large squares from the four corners, then the base of the box, which is the base like this, but you can also see it in the original picture. This will be the base of the box. This will be much smaller if we cut big squares in each corner, but the reward for doing that is that the height of the box, it will be higher in exchange. So there's kind of a push and pull here between the base and the height, and we need to find the ideal situation where base times height is as big as possible. So we want to set up a function for the volume because what are we trying to do? We're looking for the maximum volume. So we're looking for where the derivative of the volume is going to be equal to 0, and it is a maximum. The formula for the volume is base times height, which we can write as length times width times height. Now we want this to be written in terms of a variable we can work with, and a good choice happens to be to pick x as the side of the squares we cut off. So we have x here, we have x here, and we have x here, and all around. X here, x there, and finally x here and x there. That allows us to realize that the base of the box, which the base, as I said earlier, is this rectangle here, has two sides that are 20 minus 2x and 25 minus 2x. These 20 and 25 come from the size of the original pieces of cardboard. So we have all the values here, 20 minus 2x, 25 minus 2x, and x. When we place these values on the box itself, this is what it looks like. So we can multiply 25 minus 2x times 20 minus 2x times x and get the volume of the box. It is very convenient here to distribute because when we have a polynomial, it is so easy to differentiate. V equals 4x cubed minus 90x squared plus 500x, and the derivative is v prime equals 12x squared minus 180x plus 500. So when is that maximum? The volume is going to be maximum either when v prime is equal to 0, that would be a horizontal tangent line, or when v prime is undefined, or at the endpoint. So we're going to look at these three areas where the candidates are going to show up and then compare all the solutions. Firstly, v prime equals 0. So it's a quadratic equation equal to 0. One way to do that is to use the calculator. Just in case it's a non-calculator exercise, it wouldn't be here because, like you can see, the answers are rather complicated. But it could be that in another exercise, you have to either factor the quadratic equation or use the quadratic formula. So keep in mind the quadratic formula can be useful sometimes. I will say that this exercise is a little bit of a mix, an unfortunate mix between non-calc and calc, because if this was a calculator exercise, then we could just graph the function and find the maximum. So we're kind of pretending it's non-calc until we wrote the quadratic equation, and then we use a calculator to figure out the values of x. We get two answers, x equals 3.681 and 11.319. One of these is not possible, and it's the 11. This is where these word problems are interesting, because we have to always keep in mind the context. And the context here is that we have cardboards that are only 20 centimeters large. So how could I cut two squares, one from each side, both being 11 centimeters long? It's just too much. 11 centimeters from this side and 11 centimeters from that side would overlap, and we wouldn't even have a box anymore. So we have to discard this as an impossible solution. Secondly, I'll come back to this later. Secondly, when is v prime undefined? It's never undefined because this is a polynomial. Lastly, the last candidates we need to check are the endpoints. And again, because this is a real-life problem, there are endpoints that stem from just the situation being what it is. What is the minimum value x can ever be? It's 0. It would be kind of an unreasonable choice of not cutting squares and pretending we have a box that is 0 in height. And the other endpoint is cutting the biggest squares possible, which is 10 centimeters. We would cut a 10 centimeter square from this side and then a 10 centimeter square from that side. So the two squares would touch each other. And again, we wouldn't really have a box anymore. We would have nothing to, or not much, to fold. So in both of these cases, we can either think of what the shape of the box would be, or we can still try and plug in x in the volume. We would find that the volume is 0. So out of our three candidates, this is our first candidate, this is our second candidate, and this is our third candidate. We find the volume for each, and we realize that the maximum is v equals 820.528 cubic centimeters. If you want to have three correct decimals here on your calculator, make sure that you keep a lot more than 3 for the value of x. You should keep 6 or 7 to be really safe. Or ideally, you keep the exact value from your calculator. So, conclusion, since it's a word problem where you want to write a sentence, the absolute maximum volume is 820.528 cubic centimeters, and that happens when we cut squares that are 3.681 centimeters for each side. Second situation. A cylindrical can is to have a volume of 1 liter. What dimensions use the least material? If you know cans from food, they have different shapes. If I think of a tuna can, it's typically not very high compared to the radius. And if I think of maybe corn cans are much higher compared to a tuna can. So which of these, if we want to put 1 liter of tuna or corn in a can, which shape will have the minimal material? That's a very interesting question, probably, if you want to save material if you make massive amounts of cans. So to start, we need to know that 1 liter is 1,000 cubic centimeters, and then we are going to try to find an equation for the area. So the area is the area around, but also the top and bottom. So I would start by figuring out what the area is, and the area around is 2 pi r times h, so 2 pi r times h. The area of the bottom is pi r squared, the area of the top is pi r squared. So the area is 2 pi r squared plus 2 pi r h. Now we have an interesting information here. We know what the volume is, and that's going to help because currently in this expression I have r and h. And I want to avoid that as much as possible. I want to avoid having multiple variables. We want one variable, if at all possible. So given that I know the volume of a cylinder is pi r squared h, I can use the fact that we know this is 1000. 1000 equals pi r squared h, therefore h equals 1000 over pi r squared. And I can substitute h in the formula for the area. I get a equals 2 pi r squared plus 2 pi r times what used to be h, now is 1000 over pi r squared. The r's cancel out a little, and it is very nice to have them as r to the negative 1 indeed, because now we can use the power rule rather than the quotient rule. So a equals 2 pi r squared plus 2000 times r to the negative 1. There's no pi in this term. Once again, we are going to look for the three candidates and compare which one has the least a value, so least value for the area. First, for what values of r is the derivative equal to 0? We have 2 pi r squared plus 2000 times r to the negative 1. I need to calculate the derivative of that. It is 4 pi r minus 2000 times r to the negative 2. So I set this derivative equal to 0. I think ideally you could have this line written out there before listing the candidates, but anyways, it's 0 equals the derivative. So we solve for that, and we get eventually r equals 5 times 41926 centimeters. Then, the ADR undefined, it happens when r equals 0, but if you think about a cylinder that would have a radius of 0, it's not even a spaghetti. It would be infinitely thin, and in exchange it would need to be infinitely high to have a volume of 1000 cubic centimeters. So that just doesn't make sense at all. And finally, the endpoints. There is the endpoint r equals 0, but we've just noticed that makes no sense. And in terms of r getting wider and wider, then there is no upper boundary. R could be 1 kilometer wide if we wanted, but then the height of the cylinder would be minuscule, and it would certainly not be very good in terms of minimizing the material. Obviously, it would be two huge circles that would be the bottom and the top. But there is no upper boundary, so there's only one endpoint, the endpoint on the left side. R equals 0 is an endpoint, and then on the right, r can be as large as we want. So we only have one candidate really, r equals 5.41926, and this is indeed the value for the minimum. So r equals 5.419 centimeters. To find the h value, it's using the formula here. H equals 1000 over pi times 5.41926 squared. We get 10.838 centimeters. Notice that there is quite a relationship between r and h. In fact, h is twice the radius. What that means is that h is equal to the diameter. So the ideal can has a height that is equal to its diameter, which means if you look at it from the side, it should look like a square. This would be a square if you look from the side. I didn't calculate the volume here because of course we know the volume is 1000. This was one of the requirements. And if we really wanted to make sure that this is a minimum, not a maximum, then we would want to study whether dAdr changes from negative to positive at r equals 5.41926. So making a number line. But in this context, I think it's very clear. Even though in a test or a quiz I would write it, and in the AP exam I would definitely write it, it's very clear that this has to be a maximum, because either the spaghetti or the super flat can have huge areas, so the one in between needs to be the minimum. Lastly, an exercise that is a bit shorter, that is more mathematical. This time we are studying the curve y equals sine x, so this wave, and we are wondering what is the biggest rectangle that I can put under the curve. So it would touch up here, touch over there, and then the one side of the rectangle would be along the x-axis. What is the biggest rectangle I can make? So you can see I could have one that is very low in height, but that has a very wide base, or I could have one maybe here that has a large height, but the base is much smaller. So what is the best I can do, again, between these two extremes? So the area of a rectangle is base times height, and it's not that obvious to notice that if I call x the value here, then the base of the rectangle is pi minus 2x. Why is it pi minus 2x? Because from 0 to here we have a length of pi, and then we are subtracting x on this side and x on that side. There's a symmetry. This is x, therefore this is x. What is the height of the rectangle is also something students don't find very obvious, but the height at x is just a y value, so it's sine x. And therefore the area is base times height, so pi minus 2x times sine x. So we can find the derivative, and it's a product rule. A prime equals negative 2 times sine x plus pi minus 2x times cosine x. With a calculator, we can search for all candidates. So where is a prime equals 0? We find this value of x. When is a prime undefined? You want to develop your skill at figuring this out. A prime is never undefined because sine x is always defined, and pi minus 2x is always defined as well. So there's no issue here. It's never divided by 0. There's no square roots. There's no tangent function or other functions with asymptotes. The endpoints are x equals 0 and x equals pi. These are the two extreme situations where x is so small that the rectangle has no area, it's just a line, if I can say, or x equals pi, which is the same situation in fact. If you argued with me that the endpoints were x equals 0 and x equals pi over 2, so you would say we are only going from x equals 0 to x equals pi over 2, I would say great. That's a perfectly reasonable way of thinking. The other endpoints is right in the middle, where the rectangle is just going to be a vertical segment with no width, and the area in that case is also 0. So very good if that's your interpretation of the second endpoint. We have three candidates, this one, and this one, and we plug in the value in the formula for A each time, and we see that the largest of all is 1.12219, and that is the maximum area. There is no unit in this exercise, so we can just say the maximum area is 1.122, and that's it. If you want to add that this happens at x equals 0.710, fine, but it's not necessary. Thank you very much.